As reinforcement learning agents grow more sophisticated, their deployment in real-world systems, self-driving cars, industrial automation, healthcare decision support, demands not just performance but trust. And trust starts with transparency. But most current methods for explaining RL agents focus on single-step decisions. Why did the agent choose this action in this state? That's useful, but it misses the bigger picture. What we really need is an answer to a deeper question. Why did the agent follow this entire path and not another? This is the core challenge of trajectory-level explainability. In safety-critical domains, knowing why a self-driving car took a particular route, rather than just why it braked at an intersection, can mean the difference between confidence and concern. Yet existing approaches fall short. Some summarize behavior by selecting high-impact states. Others cluster trajectories or train surrogate models. But none consistently identify the optimal path from a messy mix of successful and failed experiences, especially when the agent is still learning. Our work addresses this gap with a principled, causally grounded framework, importance-based trajectory analysis. We introduce a novel state importance metric that goes beyond the classic Q-value difference, delta S, which measures the potential gain from choosing the best action over the worst. That's important but incomplete. It doesn't capture how committed the agent is to its chosen path. So we augment delta S with a new component, a radical term RSA, that quantifies the agent's affinity for reaching its goal. After exploring several formulations, normalization of Q-values, temporal difference errors, policy entropy, and more, we found that the most effective was a value-based goal proximity metric. Specifically, we use the normalized state value function. RS equals VS minus Vmin, Vmax minus Vmin. This isn't arbitrary. It directly encodes how close the agent is to the goal, based on its own learned value function. As the agent progresses, VS increases, so RS grows, signaling that states closer to the objective are more critical. We combine this with delta S to define our full state action importance. ISA equals delta S times RS. This creates a richer measure of state criticality. Not just what could go wrong, but how much the agent cares about not going wrong. Now, to explain entire trajectories, we aggregate this importance across all state action pairs in a path. For a trajectory tau equals S0A0, S1A1, SDAT, we compute. Tau equals 1/tau times sigma, SA tau I, SA. This allows us to rank hundreds or thousands of collected trajectories and identify the most salient ones, those that represent the agent's best strategy. But the real test of explainability isn't ranking, it's contrast. Can we show that the chosen path is superior to alternatives? So we generate counterfactual rollouts. At each state along the top-ranked trajectory, we forbid the original action, force the agent to pick a different one, then let it follow its policy from there. This creates a set of alternative paths. We then compare these counterfactuals to the original in terms of reward, length, and crucially, importance. If our method works, every counterfactual should be worse. That's the ultimate why this and not that explanation. We tested this in two standard OpenAI gym environments, Acrobat V1 and Lunar Lander V2. In Acrobat, success means swinging the pendulum up in as few steps as possible, shorter is better, and rewards are negative. We rank the top 5 trajectories using different radical terms. The classic delta Q-only method selected paths with average length 70 and reward minus 69. But our V-goal metric, 68.8 steps and minus 67.8 reward, consistently better. Now in Lunar Lander, the stakes are higher. A successful landing gives a reward over 200. Crashing or running out of time, max 1,000 steps, gives near zero or negative scores. Here the difference is stark. Classic delta selects trajectories that hit the time limit, long, meandering, failed attempts, with average reward around 117. But our V-goal metric, average reward of 207.13, average length 319 steps, clearly successful landings. Why? Because it's not just about action variance, it's about goal progress. The agent's own value function tells us where it's heading. And our metric uses that to filter out the noise. Now the counterfactuals. In Acrobat, when we generate alternatives from the trajectory selected by V-goal, every single counterfactual is longer, worse than the original. But for the classic deltic method, some counterfactuals are shorter, meaning the original path wasn't actually optimal. The explanation fails. Same in Lunar Lander. V-goal's original trajectory is robustly superior. All counterfactuals yield lower rewards. Classic deltic, not so much. Some alternatives beat the original, meaning the method picked a suboptimal baseline. This isn't just a statistical edge. It's a conceptual victory. Our method doesn't just identify good trajectories, it justifies them. By showing that any deviation leads to worse outcomes, we provide a human understandable, contrastive explanation. This path was chosen because it's the best possible path. This framework works best when agents are still learning, when the experience buffer contains both success and failure. But even for expert agents, the idea can evolve. Instead of ranking entire trajectories, we could identify the few pivotal states within one optimal path and generate counterfactuals from just those. Future work includes extending this to cases where the agent's policy and value function are unknown, using inverse reinforcement learning to infer a reward function from behavior, then applying our importance analysis to explain the inferred policy. In closing, Trustworthy RL isn't just about making better decisions, it's about making explainable decisions. Our framework offers a scalable, principled way to answer the hard questions. Why did the agent follow this path? Why not the alternatives? Why is this the best choice? By combining Q-value advantage with goal affinity and grounding explanations in counterfactual reasoning, we move closer to deploying reinforcement learning with confidence, not just in performance, but in understanding. This is not just a tool for debugging. It's a foundation for responsible AI.